Welcome to Lecture 8 for Physics 4C. In this last set of lecture videos on physical optics, we finish up our coverage of optical interference phenomena with the examples that find many practical uses, particularly in physics research. First, when we started our study of interference, we didn't quite have enough time to talk about coherence of light, so we do that now. It is a kind of standalone topic, so it didn't hurt us that we didn't cover this last week. And as an immediate application of single-slit diffraction pattern we covered in the last lecture, we will talk about the Rayleigh criterion, which is used to establish the diffraction-limited resolution of an optical device, or anything that spatially resolves two or more wave sources. Again, the last lecture was kind of long, so we cover this now. And we will spend the rest of the lecture talking about multiple-slit interference pattern, how to calculate the intensity pattern using the tools we have introduced so far, complex exponential math and SageMath, and the diffraction grating, which is the most practical example of the multiple-slit interference pattern. We will take a little breather next week, looking at examples of optics problem solving in preparation of the timed assessment. And then we'll have the rest of the semester for our modern physics coverage. They should have addressed this point about coherence, that for or lack of coherence could be a potentially limiting factor in whether you can observe interference effect or not. Let me see here, coherence. Yeah. So they do talk about coherence here, and, so there's some information there, and what I want you to do here is, so you see the word description here, and I think the kind of the downside of it here is that it's well. I wanted to give an alternate presentation where if this word description about coherence or incoherence makes sense, then great. Good. I guess what I'll do for the next 5 minutes or so, you don't really need it. If this didn't make immediate sense, then I want to kind of illustrate it. And this, by the way, also connects to the nature of unpolarized light. And as we are talking about interference, so that's where kind of the unpolarized light being unpolarized, that is one of the features of incoherent light, because when a light is unpolarized, the way it's unpolarized is each given kind of burst of light does have a given polarization, but it randomly shifts, and that random shift is what results in the things that you observe with unpolarized light. So the demonstration that I thought would be useful for illustrating circumstances where you get coherence, I thought laser simulation would be great for illustrating that, because in fact coherence is a special feature of laser light. Most light sources in the world is not coherent. In fact, there are very little things we can do to make natural light sources coherent. They come incoherent and they're just going to remain incoherent. It's with the lasers where you can actually produce coherent light, and it has to do with how laser operates. It's something that we unfortunately won't take a lot of time on. I think your textbook does have a chapter on lasers or section on lasers. I recommend that you read it. Wait, does it not have anything on lasers? Oh, wait, there it is. Yeah, lasers. So you can also talk about lasers and let me talk about atomic structure, because that's the place where we would be equipped to talk about how you get the light amplification. So I'm kind of jumping ahead to a topic that designated for later in the semester, in the last third of this class. Yeah. So, so this is a simulation that what I want to show here is, let me start out with, I think I can do this with the multiple atoms. So let me shine some light. And here you can kind of see what the normal sources of light or normal, natural, non-laser sources of light look like. Let me start the simulation, pause it. So you see these atoms or models of atoms emitting light. They emit light when they undergo transitions. You know, the incident light, it excites these atoms from level 1 to level 3, and as they decay down to level 2, and as they decay from 2 to 1, that's when they emit light. And these light that these atoms are emitting, they are random. Um, so the this light that one atom emits doesn't really have any relationship with the this light that another atom emits. So this is where you get randomly shifting phases and randomly shifting polarization. That's the source of incoherence. It's things that are incoherent because they have no relationship to each other. And so they, so you wouldn't expect them to be related, and they are not related. And even for the lights that are heading the mostly the same way, let me see if I can capture some of that. It's kind of hard to capture here. Let me see if I can do that with a stronger light. So occasionally you might these two uh, light particles, they're going mostly the same way, but they still have no relationship to do with each other. They are still not related to each other in terms of phase or in terms of polarization. That's the source of incoherence. That's where you get things that are just randomly distributed. And um, and when you have things when you have that incoherence, that when you can see interference, because our ability to observe interference, it relies on there being a stable phase relationship that lasts for some appreciable amount of time or length of light transmission, so that because what we observe is always a time averaged quantity, and we need those interference patterns not to be washed out in the time average. So now laser is special in that it can produce coherent light. And you kind of see hint of that. I've been trying not to bring attention to it. This simulation is designed so that sometimes it shows these doubled light particles. And these two photons they are related to each other. They have the same phase, the same polarization. They are copies of each other. So laser is a device that's designed to amplify situations like this. So let me set just to change this simulation so that it'll show the lasing condition. To do that, I need a metastable state, and I need a mirror to kind of trap that in for a bit. Um, let's see. It's been a while since I played with the simulation, so I don't know the exact parameters that'll work. Let me give this a little bit of a try. Um, oh, wait, I did this wrong. Lifetime for 2 should be long to be metastable. Okay. Um, all right. Yeah, so I think I might need a better reflectivity. Okay. Yeah. Okay. So what you have here is what's called a population inversion. In thermodynamics or statistical mechanics, it's normal for lower energy levels to have a more number of higher population. And in the laser setup, you invert the population with some either convenient arrangement or whatever, so that a state with a higher amount of energy actually has more population of atoms in that state. And when you have enough of this, you can get um, more of what's called a stimulated emission. So see if I can capture that. Okay, I think it's one of these two particles will hopefully hit either this or this atom before they decay. Then you will see stimulated emission taking place. Yeah, so this is just to hit that too. Let me, and I think, did that just appear with that? No, I think that just decayed on its own. Let me see if I can find the one there. I'm looking at this, hoping that this will get stimulated emission. No, I don't really necessarily know the details of. Okay, I'm just watching at this one, seeing if this will get undergo stimulated emission by either one of these two. No. Oh wait, there it is. Yeah, when that one photon hit this, it went down to level 1, and there were these 2 additional photons that came up. That's the phenomenon of stimulated emission. And when that happens, that's when you get light amplification. That's the LA of laser. And so the special feature here is that these 2 photons have the same characteristics, same phase, same polarization, same everything. So in a laser, you end up with a buildup with light that's basically um, light that's copies of each other. So that's where you can get coherence. These light that's being emitted out here, they have a stable phase relationship. So the light that's coming out at about the same location, they will have the same phase. That light that's out here, the phase difference from here to here will be predictable through as a fraction of the wavelength. So that's why when you see me doing interference demos in the lecture, you will always see me doing that with the laser, because it's just easier with the laser. And now you can do interference demos with normal sources of light. People have been doing interference experiments well before lasers were invented. But what they had to make sure it was, they had to make sure that their experimental setup was within the coherence length of the light source that they were using. Usually the longer lived states and narrower lines, they are associated with the longer coherence length. So so with you can do interference experiments with the sodium lens. You just have to take some precautions, take measures to ensure that that the kind of the experiment you are trying to set up is within the coherence limit of your light source. So that's why when we present the double slit interference, we present it this way. It's a single slit here. Young needed that in order to make sure that his light source from this point on is more or less coherent. Because it's such a small slit, it only lets a small portion of the light through, so that he could rely on some kind of a coherence relationship between light that's arriving here and here. So when we use the lasers, that avoids the need for this single slit, because when we have a coherent light to start with, then we can just have that and have it go through double slit. This is the purpose of what we were doing in the last 2 weeks. It's you could call it by the first thing I wrote, Rayleigh criterion. It's a good proper name to search things by. The other way to call it is it's referring to a kind of resolution limit. So this is section 4.5. I thought it had the word limit in there. So you are looking at resolution. Most people here are familiar with the word resolution, not New Year's resolution, but high resolution, low resolution, dots per inch, DPI. So when we talk about resolution, we are looking at
can you resolve, tell apart between two things? So how many here have 20/20 vision? Some of you without eyeglasses probably. When you've heard the phrase 20/20 vision, right? Yes? What does 20/20 mean? So it's usually said so-called 20/20 vision is actually 20, I guess, over 20 vision. Like, what do these numbers refer to? Yeah, size of the object at a distance. So I think if I'm remembering this correctly, what this means is you can resolve 20 millimeter difference at 20 feet away. What it means, so suppose I put two lines super close to each other. My lines are kind of thick, but imagine it's a very thin line, and I put another line very close to it. Is that right? Maybe. I may have to review it. And if the second line is very far away, then you can tell that there are two distinct lines. As I move this line closer, at some point, whether you can tell that these are two distinct lines instead of one depends on your vision. So these are something like 5 millimeters away. I think I must remember something wrong, because 20 feet away is, maybe it's supposed to be 20 meters away. Because isn't this like 20 feet? And I can tell those are two lines, and my vision is a little bit worse than 20/20. So let me just say, the exact numbers are in question, but that's what resolution means. It's so given a particular size of one thing, its angular size depends on how far away you are. So your ability to resolve things, see things, depends on really what's called angular resolution. Okay? And what we are going to go over in the next 10, 15 minutes or so is that this resolution has a fundamental limit. And this is going to be a common theme that you will hear from this point on in this class. So this is actually the biggest discovery in modern physics. That so in classical physics, these two things, you could theoretically resolve them to an arbitrary precision. It was a matter of making your lens precise enough, and just making measurements precise enough. There was no fundamental limit to how small of a thing that you could resolve. But what the wave optics, what the wave nature of light tells you is that there is a fundamental limit. There's a particular size of thing that you can tell apart, given some physical characteristic of your measuring device, and that's it. Your most ideal device cannot have a resolution that's any smaller than that. That's what this, the second phrase that's written here, diffraction-limited resolution is. That is the fundamental limit of resolution. When you have a particular optical device, a telescope that has a diffraction-limited resolution of, I don't know, a microradian, I'm making up a number, then it doesn't matter how well you manufacture the telescope. Based on some basic physical parameters, no matter how well you make it, it'll never be able to resolve two things better than that microradian. And it's based on this simple idea that you have actually seen before. So you've done the diffraction lab, right? So if I have this beam of light, right now it has a particular size. Let's say, it's small enough. So let's say this represents an ideal point, a spot with an arbitrarily small size. Now, when I make this light go through one of these apertures, one of the single slits, then this ideal, very narrow, very precise thing to point at things broadens, it becomes broader. So when I So when I put it through, I guess a third, the smallest slit, that you can see, so you see that it spreads out. But if you choose to focus on the central maximum, then it didn't spread out that much, right? But as you make the slit smaller and smaller, this central maximum will spread out more. You have, so yeah. So if I use a slit that's half the size of the other one, then it broadens out to about double of what it was before. And if I make the slit even smaller, then, so this is now the central maximum. So let me just, so this is the central maximum. Compare that to the spot that was there before I put this slit in. So, so this is the result of the single slit diffraction. And that's what we mean by diffraction-limited resolution. So before the ideal ray optics, geometric optics idealization, we would say this spot is here, like ideally at, with an arbitrary precision. Like you could describe this as small as you wanted it to, in theory. What physical optics tells you is that when this light comes from a particular slit of a particular size, so this one, I think you guys measured it to be like 0.1 millimeter, then that results in this slit being, results in this light spreading out. And that's going to limit your ability to resolve two different things. Imagine you had two laser pointers pointing at some angle through this slit. Then they would be separated by this much. And if it was going through a larger slit, then you would have been able to separate them. So when you have these two things going through a larger slit, then you will be able to separate them. But when it's going through a smaller slit, then, sorry, I can't actually do it. But you can imagine that as this spreads out and as this red beam spreads out, that they will start to overlap, that you won't be able to tell them apart. So this is the question. What is the smallest angular size that you can resolve with, let me use this phrase, diffraction-limited optics. You can actually quickly derive this relationship from what you know about single slit diffraction. So let's say you have a single slit here. So you have some light that's coming in through this single slit. Here's some light that's coming in, spreading out. And when this light hits this screen here, you get an intensity pattern that looks something like this, right? You've seen this pattern. And this is what we have been calling central maximum. And this is the picture I want you to imagine. If you have a second set of light that's coming in from different angle, so if this is coming from a source here, this is coming from a source here. And this would diffract through, and it would cast intensity pattern here. And so if they are separated far apart, then it would look something like this. So one maximum here, one maximum here, you'll be able to tell them. So call that the angle delta theta. And the question is, as you move this closer, as this source here moves closer to this source here. So, let me just, oops, I'm mixing up colors. So this is my angle theta. As you move this angle theta close, what is the point at which these two overlap enough that you won't be able to tell them apart? You won't be able to tell that this central maximum is separate from that central maximum. And this is the place where we are going to use a somewhat arbitrary criterion. This is called Rayleigh criterion. So it's arbitrary because it's a gradual thing. I mean, when they're very far apart, you can tell them. When they're right on top of each other, you can't. As they begins to separate a little bit, can you tell them? It's a sort of, there's not one point where you would say they are clearly distinct and they are clearly not distinct. So the somewhat arbitrary criterion that we are going to have is this one. When the middle of the central maximum of one of them overlaps with the first diffraction minimum is when we are going to say that's the angular size, that's the smallest angular size we can tell apart. So when your intensity pattern looks like this is when we are going to say that, so when this central maximum falls with this first diffraction minimum is when we'll say that's the smallest angular size. So this is my theta mean. And this is what we call Rayleigh criterion. So do you guys know how to derive this minimum angular size then? What would you need? Okay, what physical parameters would you need to know? Now, do you need to know the distance to the screen? Because I'm talking about the angular size. Oh. Yeah, I do want the screen to be far away. I do need to know the size of the hole. Let me call that A. What else do you need to know? So this is the aperture. I guess that's why we're calling it A. You need to know the wavelength. Okay, so the wavelength, lambda. I guess that's it. So in fact, this theta mean, it's the angular position of the first diffraction minimum, right? So, well, the equation for the diffraction that I remember is for destructive interference. A sine theta is equal to, n lambda. For the first minimum, n is going to be equal to 1. So it's A sine theta is equal to lambda. I'm dealing with a small angle here. So I can say my theta mean is approximately lambda over A. So this is what Rayleigh criterion would say for one-dimensional slit, as in, slit, one-dimensional aperture. When you actually look up the Rayleigh criterion in your textbook, there's going to be a small number here. It's going to be lambda over 1.22a. It's what you see when you scroll down. And that's because most of the times when you're dealing with the optics, you're not dealing with the slit. You're dealing with a circular aperture. So instead of this kind of overlap, you are thinking of this kind of overlap. So that's where this factor of 1.22 comes from, at least I'm told. I've never actually, wait, sorry, I put 1.22 wrong place. Factor of 1.22 probably goes on the numerator. So anyways, that's where the factor of 1.22 comes from. But even the ratio of wavelength to the aperture size, slit size, gives you the rough idea of what the minimum wavelength is. Oh, sorry, minimum angular resolution is. Yeah? So let's try this exercise. I think we have enough time to do this, and it'll be useful to do it. That's why I kind of want to do it. By the way, your textbook, this is what we just went over. This is what I want to do. So I want to just calculate the diffraction-limited resolution for some common or some exemplary object. The most common one will be your eye. And the next one, let's say telescope. I just want to see what the diffraction limit. So let's say for your eye, let's say you are dealing with someone who has 20/20 vision. So you are dealing with someone who has whose theta mean. So this is their resolution minimum. And am I remembering my numbers correctly? 20 millimeter separation over 20 feet distance. Does anyone here? Is that the actual meaning? Okay. So theta mean, if I'm remembering that correctly, it should be 20 millimeters over 20 feet. And I don't want to do the unit conversion, so let me use Wolfram alpha. 20 millimeters over 20 feet. That'll be 0.003 radians. Seems kind of big. 0.003 radians. And what I sort of want to figure out is, yeah, I'm pretty sure I'm remembering that wrong, sorry. 20/20 vision. At distance of 20 feet.
Isn't the first 20 as well?
Yeah, so I'm remembering 20 feet correctly. But they're supposed to be, okay, well, let's just do this estimate and we will deal with me misremembering optometry stuff later. Yeah?
Are you using the small angle approximation there to get the radian? Because
Yeah.
you want the angle, oh, okay.
Yeah, I'm using small angle approximation. So it should be arctangent of that, and yeah. So that's the angular size of something 20 millimeters in size at 20 feet away. And let's just see, given the typical wavelength, 500 nanometers, what the size of the size of your pupil, the aperture for the eye should be. So this is equal to wavelength divided by the pupil size, diameter. I'm going to ignore the factor of 1.22 because it's not that significant. So so pupil size, D, is equal to 3 times, wavelength. So 500 times 10 to minus 9 meters divided by that angular size, 3 times 10 to the minus 3 radians. So it's 500 divided by 3, about approximately 200 times 10 to minus over 10 to minus 3, so about 10 to minus 6 meters. So working at the unit, it should be about 0.2 times 10 to minus 3 meters, or about 0.2 millimeters. How big do you think the pupil size normally is? Like when you're out in the bright daylight sun? Like half a centimeter? I guess that's on the big side, right? So your pupil size is on the order of millimeters, right? And this is what this physics calculation is saying. What's considered to be normal human vision is within an order of magnitude of what's possible just from basic physical consideration. So even if you had a perfect human being that you could have with the size of our eyes, they could not have a vision that's more than 10 times better than what our vision is. So like Superman's vision is physically impossible because, you know, it's not possible. It's not possible according to the physics we know. So that's one estimate. That's actually kind of amazing the first time you do it, that the kind of things we take for granted is actually close to the physical limit of what's possible. The other thing is, I guess, let me do two quick comparison. So I want to do a comparison of this theta minimum for a largest known optical telescope. Compare it with the largest known radio telescope. Good. So let me just set up the space here, and then so this is the comparison of diffraction-limited telescopes. So I'm just going to do the simple one, just lambda over A. So for optical telescope, what is the typical wavelength for optical telescope? What I used, 500 nanometers. 500 times 10 to minus 9 meters. Do people know what the largest optical telescope ever built on Earth is approximately 10 meters. Yeah, so there might be 15-meter one, but there's nothing bigger than 20 meters. So let's say 10 meters. So with this largest known optical telescope, I think above this size, it becomes harder to build it. You get the diffraction-limited angular size of, so it's 5 times 10 to minus 7 divided by 10. So 5 times 10 to minus 8 radians. So yeah, I was making up the number when I said the microradians. The best resolution is about 50 nanoradians. Yep. Are people here, you have heard of radio telescopes, right? Telescope that operate in the radio frequency. So I just want to do a quick numerical estimate of how precise radio telescopes can be. So let's say radio telescope. Theta means what's the typical wavelength of radio, radio waves, approximately? Centimeters, that would be what people call microwave. Let's be generous and let's say we are dealing with just like FM radio, that would be about a meter. There's a huge range. I'm just going to pick one, say wavelength of about 1 meter. What do you think the aperture, or what would you consider as aperture for largest known radio telescope is?
50 meters?
50 meters, maybe. So with the radio, there's a technique you can use to preserve coherence over a very long distance. In fact, over 2 separate radio receiving arrays. So I want to leave it to you to search it on your own. It's called a very large baseline array, VLBA. So it uses a technique to very long baseline array. And what it is essentially is, so you have telescopes all over the US somewhere. Well, it's located in the US. So essentially what you can use as the aperture size for this radio telescope array is the size of US. So rather than 50 meters, I don't know, what's the size of US? 5,000 kilometers? Give or take a factor of 10. So your aperture size essentially for the largest known radio telescope is 5 times 10 to the 6 meters. I thought it would be as good as optical. It's not. I didn't miss a factor there, right? Anyways, so even though your wavelength is much longer, using these techniques, you can get, so this would be, I don't know, 0.2 times 10 to minus 6 radians, or about 2 times 10 to minus 7 radian. So I don't know why. I should have done this calculation before. I thought this would actually be smaller. But so the technique that I'm just briefly mentioning, it uses interference. So it's easy to think that, this is the optical wavelength, this is the radio wavelength. So, it's easy to think, then this is going to be much more limited resolution-wise. But for very clever experimentalists, you can find ways to make some numbers very big. So these are some typical numbers. And I guess if you are in fundamental physics research, this is the kind of estimates that you do often. You do quick estimates based on the laws of physics that's known, because the laws of physics that tell you what the fundamental limits are, and that gives you a target. Like, this is how well we can do if everything goes right. And that gives you a starting point for estimating what kind of things you need. And what we have put off until now, when I thought I would be getting evaluated, is multiple-slit interference, which I think it takes a little bit of more familiarity with the mathematics to be prepared to go through it. So let me kind of introduce it conceptually. what kind of things change as you are considering interference from more than one slit. So let me do it this way. So multiple slit interference. And I want to actually go back to, so another way to call this multiple slit interference is to call it n-slit interference. And the kind of discussion that we are going to have, if we said that the n is equal to 2 as a special case, the discussion we are having, it should be equally valid for n equals 2 for n equals any other number. Now, you guys are familiar with the n equals 2 case, right? That's the double slit. So let's just start out with that. Let me draw the picture for double slit, and we will build on top of that, how this picture has to change as you add more slits. So let me draw that picture for double slit that you have seen before. I have a screen some distance away, and these two slits are separated by some distance d. And I'm going back to the original picture where these slits are infinitesimally small. So whatever diffraction pattern you get from a single slit, it's super wide. So you don't actually see anything that you would call single slit diffraction pattern. Then the kind of pattern you see looks something like this. Once again, I'm plotting the intensity this way. This is my axis for intensity. And so it starts from here. Something like this is what we started out with. Wow, was that only last week? I can't remember how long ago that was. Was that only last week? Yes? All right, but this seems familiar, right? And we've done, so just as a reminder of the geometry that we are considering, for light that's hitting the screen very far away, then we could consider these rays as being essentially parallel. So we are looking at this path length difference here. Let me do it in different color. We are looking at this path length difference, delta x. This path length difference led to a phase difference of delta phi of, let me write 2 pi first so that I don't forget, 2 pi times the path length difference divided by lambda wavelength, right? And whether we got destructive interference or constructive interference depended on, is this phase difference, is this equal to even multiple of pi? Is it 2 pi n? Or is it equal to an odd multiple of pi, or 2n plus 1 pi? That's what it depended on. Full cycle difference, half a cycle difference. Right? All of that sounds familiar? All right, good. So let me just write down a few formulas that we derived as a kind of place marker, as a reminder. So let's say this is my first maximum. So this happens at such an, it happens at an angular position that satisfies this relationship. D sine theta is equal to some integer times the wavelength, right? All right. And let me just lay down one more marker so that we have something to talk about. Let's say this first, or the interference minimum, it happened at a location that satisfied this relationship. D sine theta is half a cycle apart, so half integer, and plus 1/2 lambda. Good? Actually, I think we used the minus, and minus 1/2. So that m could be 1, 2, 3, 4. Good? All right, so that's what we had, the double slit. And hopefully all of this made sense and you understood it. You could even describe this intensity function as a function of theta, and all that's good. And what I want you to think about conceptually is how some of these changes as we introduce additional slits, and how some of it actually doesn't change. So let me put it this way. Let's say that we open up more slits. So one thing I'm not going to change, let me put that in a box. I'm not going to change D. I'm going to keep the separation between two neighboring slits at the same separation. Good? So if I want to add more slits while keeping this constant, what I would need to do is I would need to open up one more slit here. So there would be another additional D, and there would be light from here. Okay? Now, this is what I want you to look at. So conceptually, there are two key positions to look at. Position A, where you had a constructive interference happen, and position B, where you had a destructive interference happen. Where you had a constructive interference, am I still going to get constructive interference from all three slits? So we can think of them pairwise. It's a question of, do any given two pair of them constructively interfere? All right, so three, there's only, I think, 3 pairs. 1, 2, 3 pairs, right? Okay, so what I know about this position is that between the two neighboring slits, there's exactly 1 cycle of path length difference. All right, that's the same thing for another pair of neighboring slits, right? What about two slits that are, 2 neighbors apart? Do these two, let me draw one more light. Do these two, I guess 1 and 3, do they constructively interfere with each other? Right, Samuel, can you explain why?
Because they have the same path lengths in between the difference of path length. So it's like every part.
Yeah, so so between these two, there's the path length difference is, let's say, 1 cycle. And between these two, that's additional 1 cycle. Let me just draw auxiliary figures. So this is the reference. So this is delta x for between these two. And this is the delta x for between this. So this is the 1 cycle difference. This is not 2 cycle difference. If two slits are at 2 cycle difference, are they constructively interfering? Yeah, it's still integer number of cycles. Yeah. So when you look at light falling at this location, it turns out that all 3 pairs you can think of, 1, 2, 3, they are all constructively interfering when you look at any of those pairs. So what that means is this location that was at constructive interference, it remains constructively interfering. So it sort of remains there. So that's actually one key thing that doesn't change in n-slit interference. Whatever locations you are getting constructive interference in, that would be this location here, this location here. Whatever locations you had a constructive interference with a double slit interference, you can use those locations as constructive interference for any n number of slits. Because these were the locations where each neighbors were constructively interfering. So you add more neighbors, they keep adding with the same, same phase. So that's one key thing to remember conceptually, that no matter how many number of slits you have, the location of constructive interference will not change. Now, the picture isn't so clean for destructive interference. When you look at, okay, I'm guessing I'm not getting evaluated today. So I actually have 40 more minutes, which is good. So let's look at this location for destructive interference. So before, with the double slit, what we had here is a 0 intensity. I had 2 slits that were destructively interfering, so no light at all whatsoever. That's what I had here. Let's see if that's still the case. We can do the same exercise pairwise. So these two pairs at this location will be destructively interfering, right? All right. What about here? These two pairs, are they destructively interfering here? All right, so far so good. Let's just check the last pair. These two pairs, are they destructively interfering? Yeah, they are not. So I guess this is where you have to be careful. So with the single slit diffraction analysis, we did, pair them up and then did the analysis that way. So here, if I do this pair and then this pair, I've actually double counted the middle slit twice, right? So this is one way to think about it. When you are looking at what's the light intensity here, these two pairs, they cancel out to 0. So I have this one unpaired slit that is going to produce some intensity here. So I actually end up with where there used to be destructive interference, I'm going to have some intensity. Not as much as intensity as what I have here, but I'll have some intensity. All right, that's already getting a little bit complicated. Let me ask you this way. So I know two locations where I'm going to have interference maximum. How many interference minima do you think could I get between these two? Two? Oh, everyone just says two. Yeah, you can get two. So let's see, how do I think that's difficult to explain without a phasor diagram. It's a matter of, I've been trying to avoid using phasors, and I don't know if I want to. So if we are using phasors, these two locations, in terms of phasors, this is what, so this location, it's represented by this phasor. Phasor plus phasor plus phasor, they are all going the same direction, they add up in intensity. And the very first minimum you are going to get here, what that's going to be represented by is the phasors that's completing a triangle. So you have phasor going this way, and then this way. Good? And then the second minimum you get, it's going to be completing a triangle, but sort of turned around a little bit. So let me draw this properly. So here, each of the phasors would be at, I guess, 60 degrees. So if this is my zero reference, the first one went at 60 degrees. Second one goes at 60 degrees from that. Wait, that's not quite right. 120 degrees, I think. All right. So there's a reason I didn't like phasors. It never made intuitive sense to me. So what I'm instead going to do is, let me show you the plot in the textbook. This is the n-slit interference that you saw in your textbook. And with the 3 slits, this is the pattern that they are showing. So it's very hard to see. This purple line that I'm following here, this purple, I don't know if you can see it's purple. This purple line, that's the double slit interference intensity. And the triple slit is the red line. So triple slit is following this line. The first minimum here, and then this is the second minimum. And apparently, so where there used to be minimum, this is that unpaired slit. They call it secondary maximum. So you get that. So that's a double slit. And when you have 4 slits, in this picture, imagine adding yet one more slit here, so that you have 4 rays of light. Then when you look at these places where you had a constructive interference, what I said before is still going to be true. You're still going to have constructive interference. That's what this is showing. And there will be additional locations where you get destructive interference. You get destructive interference here. Destructive interference, this time it coincides. Because here, at this location, where 2 neighboring slits used to destructively interfere, now you can do this. These two destructively interfere, and then these two destructively interfere. Okay? So you get this, is that black? Maybe blue. Black or blue, navy pattern. This peak here, destructive. So these are the secondary maximum where, how would you call it? I guess at these locations, what must be going on is the three of them are combining in a pattern that they are destructively interfering. And no, that's not quite right. I'm not quite sure what's going on. But the key thing is you have a destructive interference here, here, here. Okay? So when you're trying to approach this conceptually, some things will work. Like where there's going to be constructive interference, your principal maximum, that you can get conceptually. I want you to get that. But I also want you to get the rest of this feature. If you're trying to work it out conceptually, at some point it does get muddled up. This is the place for mathematics. This is where we use the math for. But let me just use this to demonstrate the calculation. So just so that you have something to attach the mathematical expressions that I'll be writing down. This is the setup that that you are considering. So this is gonna be n-slit interference. So let me first draw it as a double slit, but it could change over the course of this demonstration. Separation distance d, and with the double slit interference, what you have is, okay, you have a screen here and the light that's coming from here. When they arrive at this screen, you can describe the electric field, the optical electric field at that position, as being sum of the electric field due to slit 1 and electric field due to slit 2. E1 plus E2. And I'm just going to use the complex representation because it makes certain calculations, especially here, really simple. So these two, the representation for E1, let's say it has electric field amplitude times, then it's going to have an oscillating part, and oscillating part can be expressed this way. Let's say I'm going to set my phase to be equal to 0 for E1, then this will be just I omega t. And the electric field due to slit 2 will be, it will look like this. E to the I omega t plus the phase factor V. And this phase factor will depend on geometry in this way. So if we are imagining light going out to some distance at angle theta, the phase shift that gets introduced, that depends on this path length difference, which is going to be d sine theta divided by the wavelength lambda of times 2 pi. Wait, sorry. I labeled it wrong. This part here, this is a delta x, and there's a phase shift, phi, that can be attributed to the delta x, and this whole thing is phi. Okay, so when you have a total electric field that way, you can relate the intensity to the total electric field as a total electric field squared. Now, this is the magical thing with the complex representation, which is that if what you're interested in is not, if you're not interested in the intensity as a function of time, but instead you are interested in intensity averaged over time, then the expression for this becomes really simple. It just becomes the total electric field complex conjugate times the total electric field. This quantity is guaranteed to be real, and that'll give us the average intensity.
when you use the real function description, then this mathematical operation here, it involves integral, and so this is the magical part that gets simplified a lot when you use complex exponential representation. And I can do this calculation with a few lines of code here. So I won't explain every single line because that's something that I think you should look up and learn. So let me just do a few demonstrations here. So I'm going to define some variables. Some of the symbols that I've written down here, like d, theta, and lambda, but I'm going to call it lam because lambda happens to be a special keyword in Python language and it's going to complain. So lam instead of lambda. Oh, and t. So I'm just going to put this in as I define things. They will just cancel out magically, but I'll put it in to show that if I put it, it doesn't matter. T omega. Okay, I think that's all the constants I need. And when I was playing with this earlier, it worked really a lot better if I set the domain to be real. Oops, not capitalized, domain to be real. So I'm gonna be defining my variables that way. And I can do a quick kind of calculation. So let me define phi so that I have some easy letter to refer to. Phi is equal to d times sine theta over lambda times 2 pi. Well, let me just check. Okay, so that's my expression for phi. That looks right. That's the phase difference between the two slits that comes in as a result of this path length difference. So if I'm expressing my total electric field, it would look like, so I'm just going to say my E naught is equal to 1. So I'm kind of doing this in arbitrary units. So my electric field due to first slit would be exponential of I times omega times t plus the electric field due to the second slit would be exponential of I times omega, oops, let me add a parenthesis, times t plus phi. I defined the phi up here, and program's gonna substitute things in and all that. So all right, and I can have an expression for the intensity. I average is equal to, use this magical relationship. So say A total, the complex conjugate. This is one of the methods in the program language that calculates the complex conjugate. Oh, maybe I should demonstrate that first. So when I do this, this is what it shows. So complex conjugate is simply this expression here with all the i's replaced by minus I. And I defined these to be real variables so that this expression looks simple. The program doesn't try to do conjugate of omega, which is equal to omega when omega is real. So I average is going to be complex conjugate times the E total. And when you just print this, this is going to look a little bit complicated because, you know, it's complicated algebra. Now, one of the nice things about SageMath is that it's a computer algebra system. It can do some of the symbolic algebra. So I can do something like simplify. So, you know, this calculation here returns a symbolic expression for which there's a method to simplify the expression. And that gets stored as I average. So when I do that, all right, this looks maybe a little bit simpler, but not that much simpler. Let me try this. Full simplify. There are more things that it'll do when I ask it to do full simplify. Then you get this real function, which I think that's going to actually plot the double slit interference pattern if I try to plot it. So let me do this. Yeah, I'm gonna leave that print there, and I'm gonna plot I average, and I'm going to substitute in some parameters, d and lambda. Let me just plug in some numbers. So D 1 and lambda. So I want the wavelength to be shorter than the separation. If my slit separation is like a millimeter, and my wavelength is around 1 micron, which is within a factor of 2 of optical wavelength, then this would be 1 to 0.001. That would be kind of realistic ratios. And let me plot this from theta. So this is plot as a function of theta. And looking at this, I think once the theta is plugged in, then everything will be numerical. I don't know, from -1 to 1. Oh, that's not what I wanted. I think I need to plot a smaller range. So maybe 0.1 radian to 0.1 radian, or so from -1, 0.1 radian to 0.1 radian. All right, I need to go smaller. Okay, 0.01. So from -10 milliradian to 10 milliradian, small angle. All right, that's looking reasonable. Do I want to leave it there? I think I want a smaller portion. So let me go from -0.003 to 0.003. So 003 to 003. So yeah, that's a double slit interference. And let me, so with additional slits, this is basically the idea here. So if I had a third slit, so there's an E3, then what I need to do is, let me color code this. So I'm adding E3, then what I need to do is an expression for the third slit, electric field due to the third slit. And it's going to look quite familiar. It's going to, this should have been E0. E0 times, it's going to have same frequency, e to the I omega t. And this phase shift, you can kind of see from this geometry that the phase shift from 1 to 2, and it's the same, going to be the same amount of shift from 2 to 3. So the total amount of shift here will be 2 phi. So let me add that to my total electric field. So I have E1, E2, and finally E3, exp I time exponential of I omega t plus 2 times phi. Okay, and the rest I think remains the same. So let me run this and see what I get. All right, that's beginning to look not so simplified. And oh yeah, that looks like the plot with the 3 slits from the textbook. And I have to tell you that this y-axis here it's arbitrary units. If I wanted to normalize this properly, I might have made sure my electric field is properly scaled so that this maximum is at 1. I'm just leaving this as arbitrary units for the sake of convenience. And let me just do one more slit. Now, when you are adding slits this way, at some point, so what I'm doing right now would be 4 slit interference. And doing this manually this way, at some point it becomes very tedious. So what I would like to do is program it so that I can add additional slits with the change of a few parameters. And the program here has SageMath has a function that will help me do that well, which is a function called the sum. And I want to sum it up is particularly this way. So I'm going to express each of the terms here, which is going to be exponential of I omega t times exponential of I and parameter n times phi. So, and this n will start from 0. 1, 2, and for 4 solid, it'll go to 3. And I think that zero-based counting actually works well with how this program does it. So I'm gonna build kind of an array here. This for n in range 0 to, let me just try to duplicate this one. So this be 0 to 4. It doesn't actually go to 4, it stops at 3, because the way the language works. All right, that seems right. Let me do it here. See if it works. Okay. Expression, I'm not even looking at it anymore. I probably should have stopped printing it out. Yeah, that looks right. So, so let me actually stop printing that out. And let me just, now I can just change a single parameter to the 10 slit, N slit interference. Oh, I think this is going to start taking a long time because of this full simplify. Let me get rid of that after this one. Because that full simplify is a computationally expensive thing, and at some point, maybe even now, the program will take a long time to do the simplification, and especially when we are in the end plotting a numerical function. This simplifying work doesn't make any sense. In fact, let me reset this. I'm gonna copy it, refresh it. I don't know how server deals with that, the aborted attempt, but let me just not simplify it and run it again. T not in the list. What are you talking about? Yeah, you might have something. So I think this, when I didn't simplify it, it probably resulted in an expression that that still had a t in it. So let me do one more simplification. So when you go through the math here, you know that this omega 2 will always cancel out. So I will recognize that and not even put it in, because when you do the complex conjugate times the complex function itself, it's something that's always going to cancel out. So gonna just help the program by not putting it in the first place. And now it should work. You saw that it canceled out with the smaller ends before, and there's no reason it would have suddenly. Okay, it's getting. This kind of problem happens often, which is that I think because this was a complex function initially, when it is calculation, it got the result ended up being kind of complex in some way. So let me show you. So I'm gonna just take the real part only. So when I take the real part only, then let's make sure I get something that's reasonable. Okay, yeah, so that's the 10 slit interference. And because when I took real part only, I discarded the imaginary part. Let me just go back and look at the imaginary part. One number I do like you to take a note of is that the peak here is at 100. That kind of sets the scale for the whole plot when you look at the imaginary part. So yeah, it's practically 0, but that's still enough to cause issues when you're trying to plot it. So I'm just going to be plotting the real part. So what you saw there was, so 10 slit interference, 15 slit interference. We'll take a little bit of time for it to actually work it out and display it. I hope it's not simple. Yeah, it's not simple. Yeah, so that's a 15 slit. So you can kind of begin to see how you get to the eventual diffraction grating pattern. This principal maximum gets sharper and sharper. The numerous secondary maxima in between gets smaller and smaller until they are practically 0. And let me just do a couple more for sure. I think when I was testing this out, I tried 100 and 100 worked. So let me just try it with 100. So, take a note of how this looks like. Let's see how 100 looks like.
I hope it doesn't take that long. That's why I took out the simplifying thing, but still, 100 algebraic symbols, it's a lot. So there's probably more efficient way to do this, but for the purpose of this demonstration, it's easier for me to just wait here than to come up with a more efficient way to code this. Oh, wait, finish the calculation before that. So that's with 100, and actually with a typical diffraction grating, it's common to have this n be 1000. So even here already this is becoming sharp enough that you can't really see it well on the plot. But when you try lower values of n using computational software like this, you can see how that width of diffraction grating gradually becomes something very sharp. So let me leave it here. I think this is enough for people who are interested to try it out on your own, and you can learn about SageMath yourself. It uses a combination of Python code and other open source software to do this. And if you want to install it on your own computer and play with it, it's a kind of way to learn a little bit about programming too. So Python, yeah, using Python.
You see it getting sharper and sharper and sharper. And you guys saw this in your lab. This is diffraction grating. Let me pass it out. Please handle it by the edges. There's a rule in optics. Whatever you touch gets destroyed. And it's especially true of diffraction grating. Whatever you touch is destroyed. So please handle it by the edge. What that diffraction grating is this. It's that n slit with n taken to a very large number, like 1,000. So for that diffraction grating you're holding, I think it's 1,000 lines per millimeter. So if you have this laser beam of 1 millimeter in width, as it's going through 1,000 of those slits. Can I get I forgot to take one for myself. Is there one left at the end? Yeah, there's one. Thank you. Yeah, there's more than one left. All right. So with this diffraction grating, you see two things. One, this d is usually very, very small. So the very first thing you see is that this first principal maximum is going to be at a very large angle. You saw this in the lab. When you pass this through, so the first principal maximum is way over there. That's the first order interference maximum. That's the first order interference maximum. So it's already at like a 20, 30 degree angle. So that's the one thing. The second thing is what we saw here. With a large number of n, the interference, constructive interference peak becomes very, very narrow. So essentially what you see here is with the size of this beam, the interference maximum you see looks more or less like the same beam you see in the middle, except not as bright for some reason. Yeah? I had a demo I wanted to show. So with this diffraction grating, so this is what it is used for. I guess if you take this and look at the light, you might see some lights, but so I made this device that's more designed to do that kind of measurement. If I can show how this works after the class, maybe. I think the better thing to demonstrate the use of this diffraction grating with is this atomic, I guess, vapor cell. So this is this tube is filled with the helium gas. And when I turn it on, it's going to produce a particular kind of light, neon light. And aside from having a yellow color, the spectrum of this is actually pretty unique. Let me turn off the other distracting light, and you will be able to see. I recommend that you hold your diffraction grating horizontally. So the writing should appear horizontal. And put it right in front of your eye. Look at the light. If you need to block the other lights from around it, and look for, so you will see the yellow line in the very middle that not anything, but look to your left or right. You will see other similar short vertical lines that has yellow in it, but it also has other colors in it. Can you see it? So Sungmin, where you are might be a little bit too far to see anything. But do people see those other additional vertical short lines? Yeah. So that's what this diffraction grating is doing. It's separating out the wavelengths from this according to the, this formula here. So it's it's dependent on the wavelength. So see if you can verify this. The shorter wavelength should diffract less, right? So as you look at it, the colors that's closer to the central maximum should be the blue colors. Is that the case? Right? And the red colors in the rainbow are farther away from the central maximum.
Yeah, so I found the blue one on the right side and
Yeah.
then the yellow one.
Yeah, so yellow should be right in the middle. So this exact yellow color, that's the mixture of all those different wavelengths that get separated out by this diffraction grating. So that's a diffraction grating, and we are actually going to use this or a version of this later on when we do atomic spectra lab. It relates more to quantum mechanics. But so that's the tool we are using. So I want you to take this chance to show you the tool before we use it, like a month or so before we actually are going to use it. I can tell you this. A given diffraction grating, it has a limit to its resolution of wavelength. It's a question of, so you get this pattern for a particular wavelength, and if you had a slightly different wavelength, then central maximum would stay where it is, but this would shift a little bit, right? If it's wavelength different by factor of 2, then this would shift by factor of 2. Or if it's a shorter wavelength by factor of 2, they would shift this way. So you imagine smaller changes, wavelength change by 1%, by 0.1%. So at some point, let me go back to my older picture with the slit number of 10. What's going to limit your resolution, as in how close of a wavelength can you tell apart, is going to be limited by how wide this maximum is. So you can use something similar to Rayleigh criterion, as in if the wavelength for the second light is different enough so that this peak moves over to this position where the first minimum for the other one is, then you could say, oh, that's different enough that this diffraction grating is enough to resolve those two different wavelengths, right? So I didn't go over this. I wasn't planning on going over this because your textbook doesn't do it in detail. But I think I can give you enough conceptual basis to figure out what factors matter there. Okay? So let's do that. That'll take about 30 minutes. Unless there are other questions, I think that's going to be a good use of 30 minutes of time. All right. So this is the picture I want you to consider. So let me use this 10-slit interference pattern as a good toy model to work with. So I have this 10-slit interference pattern. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm not drawing this quite right. So let me draw the interference pattern here. And what it'll look like is, so I'll have some, oops, what am I using? I guess I'll use black. I'll have some central maximum here. And let me just mark out the position for the next maximum. So something like 1, 2, 3, 4, 5, 6, 7, 8, 9 or so, and then maximum here, and then something like that. That's more or less the plot you are seeing here. Let me finish that. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops. I need to go slow. All right, something like that. It's close enough. Good? So that's the 10-slit interference pattern. And when you change the wavelengths, and you know some of this already, some features of this, how it relates to other things already. So the slit separation is D. You can, be given that or calculate it from something. Then you know that this first interference or the principal maxima are given by this condition. D sine theta is equal to m lambda. So it depends on wavelength lambda. When you change wavelength, let's say make it shorter, then the pattern you see will change. So for a shorter, bluer wavelength, you'll get an interference maximum that occurs maybe here, right? Where this will be given by d sine theta and different lambda. Good? So the position where I drew it is the place where you'd say, I can barely resolve them. So this is whatever the difference in the wavelength between these two, whatever the difference in wavelength, lambda minus lambda 1. This is the minimum resolvable wavelength for this diffraction grating. And the textbooks that cover it, our old textbook, goes out this far. It defines the power of diffraction grating. I think it defines it as the wavelength divided by delta lambda. I think that's how it defines it. Whatever it is, doesn't matter. I mean, if you ever need to know power of a diffraction grating, you can look it up when you need it. What I want you to go over is how you would figure out what feature of this 10-slit diffraction grating relates to this resolving power. As in, if you wanted to make your diffraction grating have more resolving power, be able to resolve wavelengths that are closer together, what would you change here? I mean, there's the obvious thing, increase the number of slits. But what I want you to go over conceptually is how does increasing the number of slits actually give you ability to resolve wavelengths that are closer? Yeah, so I have 8 minutes. I think that's enough time. So I want you to think more I want you to go back to thinking conceptually about this interference minima. And unlike with the 3 and 4 slit minima, once your n gets large enough, it becomes easier to talk about this interference minima. Because I can just ignore odd 1 or 2. I can just look at the extreme cases. So here's actually one extreme case. I can look at one extreme case of the midpoint between two interference maxima. That's where the original diffraction minimum, interference minimum, 2-slit interference minimum used to be. And with a big enough n, I can say somewhere in the middle here, yeah, there's a minimum somewhere there. So what kind of pairing would you do to say these pairing of slits lead to totally destructive interference here? How would you pair them up? Neighboring slits, right? Like that's how they were originally. Neighboring slits, so these neighbors cancel each other, these neighbors cancel each other, these neighbors cancel, these neighbors cancel, these neighbors cancel. And if there's an odd pair that's left out, then with a large enough n, we don't really care, because it's going to be small enough intensity that we can ignore it. Good? So that's conceptually how you get this interference minimum with the n-slit interference at the very middle between these two. I want you to go to the other extreme. So this interference minimum was, I guess, yeah, I want blue. Great. This interference minimum was as far away from any one interference maximum as you could get. So I want you to go to the other extreme where it is you are going as close to one of the interference maximum as you can get. So it's a position where you get totally destructive interference. So what that means is there must be some way to pair up these slits so that they destructively interfere. How would you pair them up? This might help. So I think this is actually a little bit harder one to look at. So the one on the other side, this one is the easier one to look at. So this is the central maximum. So we are looking at, okay, how close to the central, what's the minimum that's closest to the central maximum? And for this destructive interference to occur, how are the slits paired up? This is where having some sense of intuition helps. So you see, so this is my theta equals 0 line, right? You see the point where you had interference or diffraction minimum. So you have some kind of angular size for the one in the middle, right? And you have another angular size, theta, I don't know, closest or whatever. So this is the sense of intuition I want you to start developing. When you have an interference pattern or a diffraction pattern, you've seen different kinds of patterns in your lab, wide pattern, narrow pattern, right? When you wanted this pattern to be wide, the kind of sizes here, did it have to be narrow or wide? Narrow, right? With the double slit interference, the kind of separation that produces wide pattern is the one that has small separation. Same thing for diffraction, actually. It's the small single slit that produces wide diffraction pattern. This is going to be, if you develop this intuition, that's going to be something that helps you both with this and eventually quantum mechanics somehow. So this is what I want you to be answer intuitively. So we got this kind of pattern by pairing up slits that are as close to each other as possible. So how would we get this pattern? Pairing up slits that are as far away as possible. And this is how I'm going to propose pairing up the slits. Let me number the slits first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I would pair them up this way. 1 and 6. So I'm pairing them up and I'm arranging them in such a way that these two destructively interfere. 2 and 7, 3 and 8, 4 and 9, 5 and 10. This is the spot where these paired this way destructively interfere. So the question comes down to this. I want this position to get even closer to the central maximum. How would you accomplish that? So by greater D, you mean you want to separate out these, right? Yeah, so that is actually one way to do it. Now, one downside of this is that if you are changing D, that will also separate these out also. Yeah? So this is where adding more slits will help. Adding more slits means when you pair up, make this kind of pairing, that you get to the, closer to the maximum without changing the positions of maximum. So, if you actually have to calculate a numerical expression for power of diffraction grating, somebody can go through the derivation, but I want you to use this time to just explain the conceptual idea of, so this is one of the things that limits diffraction grating in a fundamental way, the same way we talked about diffraction-limited resolution. So yeah.